Bene, direi che possiamo partire. Buongiorno a tutti e benvenuti a questo secondo appuntamento webinar in collaborazione con Anderà. Io sono Linda Croci, uno dei responsabili commerciali di RT Environment. Ed oggi parleremo di tecnologie e di installazioni a confronto per le misure di corrente. Parlerà il dottor Anders Tengberg. Rubo solo un paio di minuti per presentarvi WOTEC. Noi siamo distributori italiani di vari marchi volti al monitoraggio delle acque, tra cui appunto Anderà e YSI. Oltre a fornire strumenti, offriamo anche servizi di noleggio, dimostrazioni e supporto all'installazione in fiume, lago e mare. Colgo occasione per informarvi che alcuni giorni fa YSI ha tenuto un webinar sulle loro piattaforme mobili di misura, tra cui la UV EcoMapper. In slide alcune foto di una nostra vecchia fornitura. Nell'email di follow-up che seguirà questo webinar troverete anche il link a materiale informativo sul webinar YSI. Bene, buon webinar, non dimenticate di scrivere le vostre domande in chat. Ora passo la parola al nostro relatore, Anders Tengberg. Anders, welcome.
Thank you.
Good morning, you can start your presentation.
Thank you. So good morning to everybody. I stopped my video to save bandwidth. Can you see my slide?
Yes.
Okay, good. Thank you for joining this webinar. I will talk about current measurements from different platforms and also comparing different types of instruments and different types of acoustic modes. And I will show you some examples from some projects we have been involved in. I work mainly at Andera as a scientific advisor and product manager. I also work at the University of Gothenburg in Sweden with oceanographic research. And I will present this webinar on current measurements, and also at the end I will just show one slide on some new sensors coming from Andera in 2021. And thank you to Vatek for organizing this webinar. So about the first slide I will present here, there is an application note on this and in comparing the different types of instruments, which is available on the web pages of Andera, and we will also distribute it after this webinar to all of you that participated. And the example I will show you is from a project that which is called Emerge, and it's about tracking pollution from ships, in particular open loop scrubbers. Open loop scrubbers, they move pollution from the fumes, from the chimney of the ships, scrubbing them off, and they pump them into the water. So pollution from running with the crude oil goes into the water instead. And in this project, we are chasing ships and looking at how they mix the water, and also how pollution spreads at different levels. This is just one example of a ship passing by. This is from measurements in August last year. And you can see here, this is from the echo sounder of small boats that we have. And here is the bubbles from the ship, how they spread over time after the ship has passed. And here is from measurements from acoustic instruments that were installed on the bottom. I will show you more results from these as we go on. So basically, since we look at the effects of ship, we work here in a strait between Sweden and Denmark. And we placed instruments under the ship lane at the different places. Here is a signature, Nortec signature 500, placed in a bottom frame in a gimbal bottom frame on the bottom, 400 meters away. We have on the bottom here, there is a SeaGuard II acoustic profiler, 600 kilohertz. And above, in a special float to stabilize the instrument, there is a signature, Nortec signature 1000. Then further in, we use data from a buoy, which has been in operation since 2016. This buoy is part of the Swedish navigational safety system, Viva, which you can download as a free app on the internet, and where there is more than 100 stations in real time, normally reporting every 10 minutes. And here is an example from yesterday of what the buoy is giving in terms of currents at different levels, going from surface 0 to 2 meters down to 18 meters, which is basically the depth for which affects the ships that are coming into this harbor here. And we also compare here with measurements of a single point acoustic instrument, which also measures salinity, oxygen, and temperature at the bottom. These instruments, SeaGuard was installed here and has been measuring. It's serviced once every year. It's measuring at 1 hour intervals, and we have data here from 15 years of deployment. So service every year. And the point of this, or the purpose of this installing this instrument here, is to look at changes in benthic fauna, in bottom fauna over time, how it's affected by changes, increasing temperatures, for example, by strong salinity changes, or by hypoxia, by low oxygen in the area. So these are the instruments that we will look into and how they compare in the measurements. First, if we see how the instruments were set up, there was the SeaGuard II at the bottom, and if you remember, it was placed here. It was set up it's placed on the bottom at 33 meters depth. These instruments have the unique ability that you can set them up to reference simultaneously to the surface and to the bottom. So the way I set it up in this case was I wanted to get the surface currents. This is just one cell you see here marked in blue. At the same time, I wanted to compare data from this SeaGuard II instrument with the Nortec instrument, which is 400 meters away, the Nortec 500. So I set it up in the same way as the Nortec. It's referenced to the instrument, profiling upwards, and with 0.5 meter cell size. Then I also want to compare what the bottom mounted instrument is giving in terms of current measurements, and compare it what the surface mounted acoustic profiler is giving from the buoy, which is a little bit further in towards land. So I set up one column which is referenced to the surface. So when the surface is varying with the tides, this one is also tracking with the tides. And I set it up in the same way as the acoustic profiler on the buoy, with 30 cells and 1 meter cell size. And then I also wanted to compare with the Nortec signature 1000, which was placed on a buoy higher up. And so I set it up in a simultaneous way as that one. It has a much shorter range, but higher resolution. And if we look then how the acoustic instruments on the buoy, the navigational buoy, was set up, they were set up in narrowband. Our sensors, they have the ability to, you can select either broadband or narrowband. Broadband is good to save power and gives you additional lower noise for the same amount of pings, but it has some disadvantages in some cases. And I said it was set up to measure with narrowband, and of course it's mounted on the buoy, so it's following the surface with 30 cells and 2 meter cell size, but 50% overlap. So basically you have 1 meter cell center spacing. In this case, as on most navigational systems or buoys we deliver, there are 2 acoustic sensors mounted on the same platform, one which makes a profile towards the bottom and one which is measuring the surface current, in this case 1 meter below the surface. That's a single point acoustic Doppler sensor, which gives you the surface currents. So why do we use narrowband on a buoy and not broadband? Because broadband saves power. The reason for that is that if you have a platform which is moving in the waves, rocking in the waves, or if you have a mooring which is shaking or vibrating, the broadband norm has problems. It would give you what we call ambiguity issues. This is related to the length of the broadband ping and how it is reflected against the particles and comes back. And here is an example of this from buoy measurements where we can shift between broadband and narrowband. Here you can see current data. This is downward looking, then starting at the surface here. And we can see that the range here, the effective range of the Doppler current profiling sensor is around 60 meters, something like that. First, we start with narrow band and 300 pings in spread mode at 15 minutes interval. Then we shift to broadband, 60 pings, spread mode. And as you can see, the data becomes very noisy. Quality is not good. And this is because the sensor is moving too much in between the pings. You get this ambiguity issues. And then we shift back again to narrowband and you get the same quality of data again. If you look just at one single cell, the first cell, which is closest to the sensor, you see the same thing here. You see clear current changes, which you can resolve very well the details in, and then you change to broadband and you get very noisy data. It's still tracking, but you see the data becomes very noisy. So as I told you, we typically on buoys and so the current measurements are done surface currents with a single point sensor and profiling currents with this profiling sensor below. And they are normally placed inside the PVC tube to be protected. So the single point is sitting inside the PVC tube and measures through the PVC tube. And then the profiler just barely sticks out at the bottom of this PVC tube. We have recently have a lot of experiences measuring currents with our current sensors from autonomous platforms, like here the sail buoy, and there we see the same thing. It's preferred to use narrowband, otherwise the quality doesn't become very good if you use broadband. So if we compare now what we had from these measurements in the strait here between Sweden and Denmark, here are data from the buoy. I just took out here currents measured with the buoy. This is the speed, and red is 1 meter below surface. That's with the single point sensor, which is working at 2 megahertz, and the others are with a profiler, which is working at 600 kilohertz. And you can see, so it's from 1 meters below surface, from 5 meters below surface, from 7 and 9 meters below surface. And then the same colors are from the same depths. And here we have progressive vector diagrams show you how the water is passing the buoy here. And here is the direction for the different depths. And you can see here that basically around the 22nd of August, we have a big shift in currents. It's shifting basically by 180 degrees. And this is typically what we have here in the strait. It's going southeast northwest direction of the currents, because that's the direction of the strait. And on this plot here, you can see the heading, how the heading changes. That's in white. You can see basically that the buoy, when you have this shift, turns the other way about 180 degrees. And also here you see the tilt. You have a period here with strong winds and much more tilt and much more vibrations. So here we have the results from current measurements from the buoy, and here we have the results from the bottom-mounted acoustic profiler, SeaGuard profiler, with working with broadband. And basically, we can see that the shift in current direction comes at the same time. We see that we have a really good agreement in the first period here, but when currents shift, the currents from the broadband, from the bottom-mounted instruments becomes higher, and this is because this is further out in the sound. So when the direction changed by 180 degrees, we see this higher currents in the bottom-mounted instrument, which is about 400 meters further out in the strait. But in the beginning, they are agreeing well. And also the direction is slightly different here compared to what we get from the buoy, and this is because the buoy is more close to the shore. So here you can also see that we had a more period with more wind. This is the bottom-mounted instrument is also measuring waves, and you can see that we have wave heights of about 1 to 1.5 meters during this period, more windy period. And if we compare then with the Signature 1000, which is just measuring the top meters of the water column, about 15 to 20 meters of the water column, with the Signature 500, which is further out, and with the SeaGuard 600. This is the north component of the measurements. And of course, here you cannot judge anything about the quality from the details. With Andera instruments, we deliver a software where you can fully plot and analyze your data. But in this case, with the Nortec instruments, you have to buy additional software to analyze the data, and you just have access to this very basic plotting software where you can just make a couple of plots. So I made the plots I could here and compare them, but I also exported the data from the Nortec so we can compare them in more detail. And what we see here is if we start first comparing surface currents in red, that's from the SeaGuard II, closer to the surface or close to the surface. In orange is from the Nortec 1000, which is just above the SeaGuard II. And in blue is from the Nortec 500, which is further out, 400 meters further out. It shows higher currents, but yeah, the same type of variations. And when currents become low and the direction becomes, yeah, we see the same pattern as for the buoy. If we then focus in on the bottom currents, which you see here, and compare the SeaGuard II profiler with the Nortec Signature, we can see that for bottom currents, they are more alike, and we can see some delays in shifting between the currents here, but basically they show similar data. Remember now that there is about 400 meters between them, and the Nortec 500 is further out in the strait. So I think we can conclude that they basically show very similar values. If we then compare what the buoy is giving, we remember we have an instrument here installed and run by the municipality, by the ecologist of the municipality at the bottom, which is serviced once every year and has been in operation there for 15 years. If we can compare what this instrument gives, but it's placed only 1 meter above the bottom, it's measuring only at one level. So we can compare with the acoustic profiler, which is profiling towards the bottom, but there we have a blind zone close to the bottom. So we can compare only cell, which is 1 meter above bottom for this single point instrument, and 4 meters above bottom for the profiler. The water depth here is about 35 meters. Still, we see that there is quite good agreement between the two in terms of direction and speed. And as I told you, with the SeaGuard II instruments comes a powerful software for plotting, for quality control. And then if you want to make more of your data, you can export them to MATLAB, for example, or CSV format. What I normally do when I get the data, I take about 1 hour to make some kind of couple of quality control plots. You don't see so much details in them, but here you see quality control parameters that I normally plot: horizontal speed, signal strength, vertical speed, standard deviation of the horizontal speed, and then some of the sensors that were mounted on the instrument. In this case, so we had temperature sensors, we had a couple of oxygen sensors, we had salinity sensor and a wave sensor. Then I can just focus in on some of the other parameters. Here is also quality control. This project is dealing with ships and the mixing from ships. You can see here from the standard deviation of the horizontal speed how the mixing when ships passes goes all the way to the bottom. So you can also see how the ship seems to have some effect on the vertical speed here. Once you've done plots like this, you can just change the timings and you can focus in on details. And here you see details from just 2 days of measurements. So in 1 or 2 hours, I have information about the quality of the data and about basic features and what happened during the deployment. I can also make 3D plots like you see here. Here we have current speed going from the bottom to the surface. Here was a windy period with much more currents and more waves. And here we have the standard deviation of the horizontal speed for the deployment. And you can see here how the passages of ships is mixing the water down, but it's when you come closer to the bottom, these effects are diminishing. But here we see a much higher standard deviation in the surface, and this was during the windy and wavy period. And still, it seems like there are some events here that travels almost all the way to the bottom. So this was an example of comparing instruments and in a project which was dealing with hydrodynamics and mixing of from ship traffic and tracking of pollution. Now I will show you a different project where we are looking at resuspension of contaminated sediments from a dump site of chemical weapons. This is off the west coast of Sweden, and this mainly here there was German mustard gas that was dumped after the Second World War by British. And there's a lot of wrecks here, but since there is wrecks, there is also a lot of structures. And if you have structures on the bottom, you also have fish. So trawlers, they pass through here and they fish. And the water depth is about 200 meters. The violet tracks that you see here, they are from bottom trawlers, just from a couple of days in April. So we wanted to see how much resuspension are the trawlers doing, how high is they resuspending the sediments, and what effects could that have on transporting contaminated sediments. So we deployed an acoustic profiler with turbidity sensors on it. And from the turbidity sensor, we can see peaks in turbidity during a 2-week period here, something like that, or 3-week period. We can see peaks in turbidity, and all these peaks we could relate to trawlers passing in the area trawling. So they resuspend the sediments, but how high above the bottom do they resuspend the sediments? Because we measured turbidity just 1 meter above the bottom on the instrument, and we want to see how high above bottom they resuspend the sediments. And yes, here you see the trawling tracks. Here you see wrecks with chemical ammunition. And here you see one wreck, for example, and how the trawlers are passing. You see the trawling tracks on the bottom. But by combining the acoustic backscatter signal strength with the turbidity sensor, we can see that these peaks that are created by the trawlers, because we measured currents, and we know currents are not high enough to resuspend sediments naturally at this site, quite low current dynamic, quite low dynamics. We see that by combining this, we can see that every peak is related also to an increase in acoustic backscatter. And by looking at this, we can see that basically the trawling resuspends sediment to up to about 30 meters, something like that, above the bottom. And of course, it's the finer sediments, it's the clay particles that are resuspended, and the clay particles typically binds to toxic substances that comes from the chemical weapons. So we combine this with looking at, in collaboration with the Swedish Geological Survey, we look at, for example, arsenic in the sediments. Arsenic was used in these chemical weapons in high amounts. And if we look at the currents measured during deployments here, in the bottom 25 meters, we can see that they are basically going towards northwest. So northwesterly currents here, and we have the dump site here. It's the black flag, and the site with the highest arsenic concentrations in all Swedish waters was at downstream of this. So what we think is happening is that we have some of the chemical weapons leaking out into the sediments as these containers and grenades corrode, and they are, and by trawlers resuspending the sediments and the fine sediments transported with the currents, you get spreading of these of chemical of toxins in that environment. So we try to ban trawling here together with Swedish authorities. We don't think they should trawl at the dump sites, but it's from a law point of view, this is a really difficult task, because it's not in the Swedish it's in the Swedish economical zone, but not inside the 12 nautical miles territory. Also, we can see from other sampling here and fishing, we can see that fish and shellfish contains low amounts of remains from chemical weapons, which you can only find in the chemical weapons. These are not arsenic you have in the nature, but here these compounds here, Clark 2 and Clark 1, are only found in mustard gas, for example. So this was a combination of turbidity, acoustic backscatter, and measurements here. With the SeaGuard instrument, you can also combine acoustic current and backscatter measurements with other parameters, like in this case here, oxygen measurements. Here is in a fjord, measuring oxygen at different levels. We have anoxic conditions at the bottom, and as you go closer to the surface, you have more and more oxygen. You can look then at primary production, for example. In this case, we see a peak when the spring bloom comes, how deep the peak goes. It's going down to about 15 meters below surface, and you can calculate then how much primary production you have in the water. And here is another example of measurements from the same observatory. And we put then on a string here, we put oxygen and salinity sensors. We also had PCO2 sensors here. And we combine them with the acoustic current measurements and acoustic backscatter measurements. And here in this case, you can see that in around January the 10 or so, we had an inflow to this fjord of more oxygenated waters. You see this curves here. This is oxygen on this graph, brown, pink, yellow, and red. That is oxygen closer to the bottom, and the others are closer to the surface here. And we have an inflow here which oxygenates the fjord and the bottom water of the fjord. And there is also a change, smaller change in salinity. Pink here is salinity closest to the bottom, and then we have the temperature measurements here. So the combination here of currents, of backscatter, of mixing, and of parameters on a string gives you the potential to study ecosystems, for example, biogeochemistry. To summarize, I showed you current measurements from different instruments and platforms, and they in a project in the strait between Sweden and Denmark, and they agreed well. We had a little bit lower currents from the buoy in one direction, closer to land, but apart from that, it's a good agreement. We had here some instruments running broadband, BB, and on the buoy it was running narrowband to avoid this ambiguity issues that you have with broadband on a moving and rocking platform. Then from platforms that are moving in the waves, vibrating, I showed you some examples there. We always recommend to set our sensors in narrowband when you use them on buoys, for example, or on autonomous platforms, because the data quality becomes much better. You don't have this ambiguity problems. Of course, to have good data quality, you should compensate every acoustic ping on a platform that moves a lot. For movements, you need to compensate for tilt. You need to have a compass, a 3D compass, which follows the movements and the heading of your sensor for every single ping, and that is what we have, and we had it for the past 20 years or so, also in previous generation of acoustic profilers. And I showed you an example of where combining turbidity and acoustic backscatter can be very useful to look at, for example, resuspension of sediments and sediment transport. It can also be a valuable information when you are doing, for example, dredging applications, where we see that many of our customers are using this combination in dredging applications, both from buoys and also from bottom-mounted platforms. And I showed you examples from this tracking of pollution from ships, where we look at combination of currents and mixing, and to look at spreading of pollution from ship traffic. And another example I showed you was from a fjord, where a string of sensors that mainly measures oxygen and salinity and temperature in the water column are combined with the current measurements and with mixing measurements to look at biogeochemical and ecological parameters. And just to summarize the features of our SeaGuard II acoustic profilers, they can run broadband and narrowband. You select that, the user select that. You can measure surface currents, which is a unique feature from a bottom-mounted application. You can set them up in multiple columns, meaning I showed you this in the beginning, where you can have surface, you can have one column, for example, following the surface, which, for example, the tides, the water level variations, and makes reference to the surface, and you can have one column which makes reference to the instrument itself. The instruments can handle tilt and compensate for tilt up to 35 degrees. We have one unique feature which is used a lot on buoy applications, and that's the auto beam. Auto beam, because on buoy applications, often you will have the mooring chain, which goes into one of the acoustic beams. Then if you set the instrument in auto beam, it will sense which of the 4 beams is affected by disturbances in the beam, and it will use the other 3 beams to calculate current, speed, and direction. And this is a useful feature if you suspect you will have some objects in one of the beams. Also, acoustically, these instruments can measure directional waves. And I showed you how you can connect different types of sensors to them. You can cover the water column with a string. We have efficient real-time possibilities from our systems. many customers, they store a lot of information on board. Buoy, for example, current profiles all the way to the bottom, mixing and backscatter information, and they only transmit the data that they need, for example, for navigational safety. So you can store most of the data if you want. You can store all the raw data. You can store all the data, and then you can transmit only the data that you need to have in real time. We have graphical software to post-process, which is included with the instrument, with 3D plots, with 2D plots, with progressive vector diagrams. And we have examples of longer deployments, 4 years at 30 minutes, for example. And finally, I'll show you a slide of some of the new sensors or updates to some of the sensors we have that will come this year from Andera. We will have a new conductivity salinity sensor with a factor of 10 better accuracy, which will be released in the middle of this year. We have a new turbidity coming out, which will fit also on strings, so you can measure at several levels and combine with acoustic backscatter, for example, and with a wide range, 0 to 2,500. We have new optodes for trace measurements. These are a little bit special measurements, but they have nanomolar resolution from 0 to 10%, so it could be of interest in oxygen minimum zones, for example. We have new foils for the deep water optodes, which are 2 to 3 times more stable than the old ones. But yeah, we still keep the old ones until the new foils are really well proven, and they have lower pressure effects than the old ones. So typically the new foils have a drift of about 0.2% per year. And we have been involved in some development projects together with one of our dealers in South Korea, developing integrated units with UV light for surface measurements. This is an optode here, an oxygen optode integrated into a unit with UV light so that you have anti-fouling protection. And our MOTOS sensor, which is directional wave sensor for buoys, has been updated with some more parameters. And our pressure and wave tide sensors have been updated with new software so that they can detect centimeter waves from 40 meters depth, which was not possible before. And with that, I would like to say grazie for listening. And I don't know if there was any questions. Shall we look in the chat?
Thank you, Anders. Se avete delle domande potete scriverle nella chat. Non pare ci siano domande, tutto molto chiaro. Thank you, Anders. Everything was very, very clear and interesting. Come detto, seguirà un'email con un po' di materiale da scaricare e per domande, chiarimenti, vi lasciamo digerire la presentazione, potete scriverci senza problemi. Anders, thank you again. See you hopefully in the future in person.
Yes, the same thing. I hope I can meet many of you in person soon as well. At this time, it doesn't look so good, but yeah, we will see.
Yeah, finger crossed.
Yes, thank you.
Okay.
Bye-bye.
Thank you everybody, grazie a tutti e a presto. Buona giornata.
Buona giornata. Grazie.